a lot. And also thank you for the opportunity of showing this work with the last year progresses on how we calculate nonlinear optical properties from first principles. So I will just give a bit of motivations behind, and then showing the how we approach this, and then some showcasing a few of results that we got in the last years. So first of all, why should we be interested in nonlinear optics? And this is just a selection, very probably personal. So first of all, there has been a revamp on nonlinear optics with research in 2D materials, since with, for example, second harmonic and third harmonic generation, one is able to just probe the symmetry, and so the number of layers, the edges, the orientation of the layers, and so to characterize and image these materials. And as well, also I was very interested in reports of exceptional strong nonlinear optical properties in some of those 2D materials. Coming to the theme of this conference, the nonlinear optics is also very sensitive to anti-ferromagnetic states, in particular second harmonic generation. So the bilayer of chromium 3 iodine or iron phosphide 3 sulfide, they will be both dipole forbidden for second harmonic generation. However, since when they are in their anti-ferromagnetic state, there is a very strong signal that has been observed. Also, I mean, there was the previous presentation, so I don't need to convince of this. Nonlinear optical properties are a sensitive probe to monitor ultrafast dynamics. So here I'm showing some results obtained also, again, with transient second harmonic generation. So here, just monitoring the second harmonic, they were able to look at the magnetization induced by the pump. Here, they were able to follow the excitation from the pump, and then the decay of the excitation into phonon mode. These are a couple of more examples. And of course, when we are in just looking at what kind of theory we want to develop, we also have to look at the physics we need to include. And for looking at those materials, there have been just several works experimentally saying, well, excitons are important. So that means that we would need an approach that includes the physics of excitons. So before delving into the nonlinear optical properties, just see what is available for the linear optics. And I will just look at lithium fluoride, which is a wide gap insulator with free fundamental band gap of about 14 electron volt. This is the absorption spectra that shows this sharp peak below the band gap, which is a signature of an exciton. So according to Fermi-Golden rule, we would have to calculate the ground state and any excited states that differ by the ground state by the photon energy. So what are we doing actually from first principle? So the very much simple approximation is that of calculating the electronic structure using the density functional theory, and then approximate the energy differences and the dipole matrices using this electronic structure. This is really an independent particle approach. What you obtain here in red, it's very similar to the joint density of states with Van Hove singularity, and you could see that the onset of the spectra is really too low, and this can be tracked by band gap problem in density functional theory. So the next step would be to just correct this, and a way is the GW approximation within the many-body perturbation theory. So this corrects well the cone-sham density functional theory energy to quasi-particle energies, and shift the onset to the fundamental band gap, but basically we are still in an independent particle. So the framework that really works to reproduce quantitatively optical spectra is those of Bethe-Salpeter equation on top of density functional plus GW. So this is a two-particle effective Hamiltonian, which eigenenergies are the excitation of the physical, or approximation for the physical system, and the eigenvectors are given the linear combination, the physical excitation as a linear combination of electron-hole pairs calculated within DFT plus GW. So as you can see, this reproduces very nicely the exciton. So what about nonlinear optics? So when we started, it was about 10 years ago. That was the situation for linear optics, while for nonlinear optics, the publications of calculations were very sparse. Mostly were at the independent particle level, and there was also not a tool that the community could access and work with. So our idea and aspiration was to extend the scheme that I've shown you for linear optics beyond the linear regime, so having a GW plus Bethe-Salpeter. So this was done in this work with Claudia Taccalite and Andrea Marini. So we start from the key ingredients of this successful recipe that gives us this very good absorption spectra. So first of all, starting from a DFT, so we have a first principle approach, then using this GW to correct the DFT electronic structure and get the quasi-particles, and then finally use this Coulomb-Ball screen exchange approximation for the self-energy, which provides such a good and such accurate excitonic energies. So this is, as I mentioned before, done within the many-body perturbation theory. And what we have done is to reformulate within the non-equilibrium Green's function framework so that we get a real-time approach. So without going into the details that you can find in this work, what we arrive at is this equation of motion for the lesser Green's function. So from the lesser Green function, in principle, one can get the polarization, so spectral properties, and also the carrier dynamics. So the ingredients that you see here in this equation are exactly the ingredient of the recipe. So this would be the zero field DFT Hamiltonian. This will provide the correction from the GW, and these two are the changes in the mean field and in this Coulomb-Ball screen exchange self-energy, and this will be the interaction with the field. The problem with this approach is that there is no trivial way of expressing the polarization with this lesser Green function for periodic boundary system with periodic boundary condition. So later on with Claudia Taccalite, we use an approach developed by Sosa to reformulate this for single particles, so Bloch electrons, for which we can then express the polarization as a dynamic Berry phase. And this is exactly the same ingredients I discussed with you before. and those single particle states are linked to the lesser green function since they diagonalize it at each time step. So now we have finally these two. We can just solve this, integrate this equation of motion and get the polarization. So we have access to different linear and nonlinear properties just by changing the input and changing the post-processing. So if we just want the second and third harmonic, what we are doing, we are inputting a monochromatic field, and then we are just do a Fourier analysis on the output signal to get the second harmonic, third harmonic, and then we repeat this for all frequencies of interest. Another thing that is interesting with our approach is that we can very easily switch the level of approximation by changing the terms that we are including in our Hamiltonian, and so we can see what is the various effects. So here I'm exemplifying it by looking at hexagonal boron nitride. So on the top, I'm showing the second harmonic intensity, and for comparison, on the bottom, this is the absorption at the frequency and at half of the laser frequency. So if we just include the zero field Hamiltonian, we get what is the independent Kohn-Sham independent particle. And then, interestingly, we can also look what happens when we include crystal local effects by looking at the changes in the mean field potential. So these are very, very small effects. They are not visible for almost in the linear regime, but they are quite visible in the second harmonic because of the sensitivity of second harmonic to external to changes in the field. Then we can add this shift, which is trivial in the linear optical regime, but renormalize strongly the spectra in the second harmonic intensity. And then finally, this is the whole Hamiltonian, including excitonic effect, and we see this sharp excitonic resonances both at 2 and 1 photon, and we see that's distinctly different from the independent particle spectra. So this, of course, is a wide gap material. So what if we go to some semiconducting material? Also there at, so here I looked at, we looked at molybdenum disulfide, silicon carbide, gallium nitride, and silicon oxide. And we observed that we can see an enhancement about 2 to 4 when we are at excitonic resonance with respect to the independent particle calculation. So then we were very surprised and puzzled when there was the reports experimentally of very strong second harmonic generation in gallium selenide and indium selenide. Those values are kind of 2 orders of magnitude larger than what is observed in the bulk, for the bulk counterpart. On the other hand, the existing theoretical works that were there were predicting values that instead were very much in line to the bulk counterpart. However, those were done in the static limit, and they were done also without excitonic effect. So we were wondering, well, maybe this huge difference of 2 orders of magnitude is due to some excitonic resonance. So then we use our approach to calculate the second harmonic intensity, both at the independent particle level and in this full GW plus beta salpeter. So for gallium selenide, in fact, we are not at an excitonic resonance when we look at the frequency of the laser. And in fact, we do not observe any substantial difference between the spectra at the two level of approximation. And so we get some value which is substantially consistent with what was obtained before theoretically. With indium selenide, we have at some structure, but again, the two spectra looks very much the same, and we get a value which is larger than what was measured, but just because probably they were at a static limit, and we look at the right frequency, just say. But anyway, we are, again, almost more than one order of magnitude smaller for both gallium selenide and indium selenide of the experiment. So then we argue that the issue was that in the experimental works, they use a bulk model to extract the second harmonic intensity from the measurement. And according to this work, we estimate that this would give a factor 30, which is consistent with the difference we observe between our calculation and those experiments. And in fact, when we were just finalizing our work, there was this new experimental work in which they used instead a sheet model to extract the second harmonic generation and got some value which was in much closer agreement with what we had calculated. So further, we also looked at third harmonic generation, in this case for 1D nanostructure. So this is, as a nanoribbon of graphene. So again, here we look at the difference between the independent particle and full approximation, including both the quasi-particle correction, which renormalize hugely the spectra, and the excitonic effects that, again, renormalize and redistribute the intensity. And we also looked at the two-photon absorption. So here it's slightly different, since we are looking at the third-order susceptibility at laser frequency. So experimentally, this can be realized by having a lens which focuses the beam, the laser beam, so that if we move the sample slightly, this experience very much different intensity. And by looking at the difference, then one can extract the third order. And this is very close to what we are doing also in the computational setup. And we apply this to hexagonal boron nitride, both bulk and monolayer. And we look at lowest exciton. So this one is degenerate in the monolayer, and there is a symmetry breaking in the bulk. And then, interestingly, the one photon, which is here in green, can only get one of these, because the other one is dark, is forbidden by symmetry. By using the two photon, one can actually instead access this lowest dark exciton, and so this is the blue curve that indeed gets the lowest exciton for the hexagonal boron nitride. So up to now, I've shown things that one can get perturbatively, but we have a real-time approach. So in principle, we can look also at extreme nonlinear optics. Here I'm looking at high harmonic generation, or we started with, in a collaboration with Caterina Vozzi in the audience. So the high harmonic generation has been, of course, explored for a long time in the molecules and atomic system. So what one observes is that one has this plateau of harmonics up to a certain cutoff, while in a standard nonlinear optics, one would expect that the intensity of the harmonics decay very quickly of about 6 orders of magnitude when going from one harmonic to the other. And this has been explained by this three-step model. So more recently, about 10, 15 years ago, has been also observed in solid state. So this, I believe, is one of the first on experiment on zinc oxide, where they also observed this plateau of harmonics. So currently, we are just studying zinc telluride. So I'm just sending a pulse of, I think, 5 or 6 cycles. I'm solving the same equation of motion, and then I just get the polarization or the current, and I post-processing to get the power spectrum. So these are very preliminary results. These are only at the independent particle level. The first things I wanted to explore, since I never pump my code so much, was whether it could just get the effect at all. And at about 0.1 terawatt on square centimeter, we starting observing some plateau. And we also observed that increasing the field intensity, we saw an increase in the cutoff. Unfortunately, there is also some breakdown that we are currently looking at. So one thing that I think was already interesting in terms of modeling this with simple model is that our spectra really converge very quickly with the number of bands. In fact, we only need to just consider the bands around the Fermi energy to just get a converged spectrum. Perspectives, so what next? Of course, in this high harmonic generation would be nice to see what is the effect of local field and excitonic effects. I don't expect excitonic effect to play a big role in the system I show, but there may be other materials where it may play a role. Then at the start, I've shown you this second harmonic generation in 2D antiferromagnetic. And there is a PhD student working on that. Unfortunately, there is a big computational bottleneck. Those systems are large and heavy. So we are just now looking at Fouquet reformulation with this, in this work, very similar to what has been shown yesterday for the phonon, but for the photon. And then very much I would like to look at transient nonlinear optics in a pump probe setup. So this concludes my presentation. So to conclude, I show you that we have a flexible tool, flexible because we have the same equation of motion, and then changing the input and the post-processing, we are able to access different spectroscopies. And then it's also flexible because we can change very easily the level of theory, and in particular, we can get excitonic effects in an analogous way that what is done in linear optics. And this, of course, I've shown you a few results for different materials and different kind of spectroscopy. Also, it is available freely to the whole community through the Yambo code. So I just take the opportunity of thank all the Yambo team, in particular Claudia Taccalite, that co-authored all the works I show you, and then Andrea Marini, Davide Sangalli, Maurizia Palumbo and Elena Cannuccia that co-authored some of the works I show you. And with this, I also want to thank you for the attention. Thank you.
Myrta, thanks a lot. So, open.